Okay, so here's what we've got today. There's something called the rate law, and there's something called the integrated rate law. So on the back of lecture notes that you all have from yesterday, you've got this handy dandy big chart, okay, that gives the summary of these different types of order, okay? So you got a zero order, first order, second order. So what that's referring to is the exponent that goes with a particular concentration, okay? So if it's zero order, that would mean that, like for example, if you know, so this is the reaction that you have on the front of the lecture note. So if we say something is zero order, that means that's the exponent that this concentration is raised to. If it's first order, it's raised to a 1. Second order, it's raised to 2. Okay? A lot of times what you're talking about is the overall order of the reaction. The overall order of the reaction is the sum of all of the exponents. Okay? So if this was 1 and that was 1 and that was 2, you would add them all up and you go, oh, the overall order of the reaction is 4. Okay? So the whole point of this is that we're trying to figure out what determines the rate of the reaction. So this is just some generic reaction, A plus 2B plus C yielding D. Just a generic reaction. We don't know what it is. We're just going to use it as a mathematical model. Now, if you were to just look at the exponents themselves, because there's a 2 in front of the B, you would be tempted to say, oh, B should get squared, because that's the pattern that we've always followed. Oh, whatever coefficient is in front of it, that's what goes as far as the exponent that we're going to put with it. That would seem like a reasonable thing. And a lot of times it is. But when you get into very, very complex reactions, that doesn't always work. And we'll get into this later about why you just can't look at an equation and go, oh, it's first order with respect to A, second order with respect to B, first order with respect to C. Sometimes, and you'll see this in the lab, sometimes you even have to worry about what the products are, because that might influence what's happening in the reaction as well, because there can be hidden steps. It's kind of like the Wizard of Oz, you know, and the wizard is behind the curtain pulling like the levers. So sometimes there are hidden reactions in this that don't make it quite that simple. So there's 2 different methods you can use to figure out what these orders are. Tomorrow we're going to learn the graphical method. Today we're going to start with kind of what is a simpler version. So what we're trying to figure out is what's the order of these reactions, what's X, what's Y, and what's Z. Now, if you look at the data table, I just replicated the data table that's on your sheet. So here's how this was actually set up. So we ran different reactions. Let me explain, and you're going to do a lab like this with iodine. So you're going to run a reaction, and you said, okay, we're going to let the concentration of A be 0.1, the concentration of B is 0.1, concentration of C is 0.05. We ran this reaction, and we measured the rate of the reaction, and we determined the rate of the reaction to be 0.010. Now, notice that this, when I type this up, I put that as molarity per liter seconds, which also could be expressed as molarity per second, and you can put molarity S to the -1. Okay, so it's the same rate function. Don't look at this and go, oh, per camp, that's moles per liter seconds. It's molarity per second. Don't flip out. It's not a big deal. It's the same thing. So then what happened? Then we said, okay, well, we're going to run reaction 2. So if you notice the difference between reaction 1 and reaction 2 is that we kept the concentration of A the same. We kept the concentration of B the same, but we doubled the concentration of C. Okay, so we ran this first reaction. We measured the rate. Boom. Timed it. We got this number. Boom. We got 0.1, 0.01. It was great. So on 2, we did the exact same thing, but we doubled the concentration of C. We went from 0.05 to 0.1. Now, what happened to the rate? Nothing. So what that tells me, I'm painting the big picture here, right? So what that tells me is that the concentration of C doesn't impact the rate. What that tells me is that C has to be present in the reaction, but it doesn't impact the rate of the reaction. So I don't want you to look at C and go, oh, C, you're not so cool. We really don't need you. You don't impact the rate. We're not saying C isn't important. If you don't have C, this reaction isn't going to take place. All we're saying is that C doesn't change the rate. Okay? It'd be like, we have to have freshmen in the school, but they don't impact this class. All right? So whatever happens to the concentration of the freshmen out in the hallway doesn't impact my reality. And I'm perfectly fine with that scenario. I have no problem with that at all. Now, you look at comparing a reaction 2 to reaction 3. Okay, so now if you look at reaction 2 and reaction 3, I doubled the concentration of B, but I kept everything else the same. But look, the rate went from 0.01 to 0.02. So what that tells me is that if I change the concentration of B, that changes the rate. Okay, so that's going to tell me that, B is going to be a player. Okay, C was just there. Doesn't impact the rate. B is a player. These are like kids that are going to be in my room. Like, okay, hey, these are going to be impactful because they're going to alter that rate. You look at what happens if we're comparing 3 to 4. Okay, 0.1, I doubled the concentration of A, and then we went from 0.02 all the way up to 0.08. Okay, that was a huge increase in the rate. So what that tells me is that whatever is happening with A, A is a player. Okay, A is a player, man, because you change A, that has a huge impact on the rate. So C is there, we need it, doesn't impact the rate. B, important, I changed B, I changed the rate. A, I changed that, whoo, big change in the rate. Okay, now here's what you're after. What you're trying to figure out is 4 things. You're trying to find the value of X, Y, and Z. What are the orders with respect to each individual concentration? And then we're trying to find K. Now, this is lowercase k. This is not uppercase K. This is lower, not upper. So what that tells me is that this is not a constant. This is going to have units, okay? This rate constant is going to change depending upon the reaction. It might change depending upon temperature. It might change based upon concentration. There's any number of things that might alter this value of lowercase k. So I need to find 4 things, X, Y, Z, and then I need to find out what k is. Now, I want to show you this process. There is no shortcut to this process. It isn't like tomorrow I'm going to walk in and go, you know, we don't have to do this, you can just do it in 1 step. Okay? I promise you, I will never be that teacher. Okay? I'm never going to be a jerk. Go, oh, here's this big, long, arduous process. No, tomorrow you can just do it in 1 step. Okay? I hated it when teachers did that to me, so I will never do that to you. Okay? But it's just kind of a slog. So here's what you got to do. What you got to do is begin to isolate variables so that you keep everything the same. Now, I am going to kind of show you the full Monty in terms of how this is going to play out. So let's say we want to find out what X is. We're just going to work down the line. Now, you cannot find the value of lowercase k, that rate constant, until you know what the exponents are. So I can't start off by finding k. I have to find the x, y, and z values first. Then I can work backwards and find my value of lowercase k. So don't worry about k. We'll deal with it. We're not worry about it now. So what I want to do is we're going to work down the line. We're going to find the value of x. So what you want to do is that you want to pick reactions that because I'm trying to find X, which is respect to the concentration of A. So I want to pick two reactions where the concentrations of B and the concentrations of C are the same, because I don't want to change two things at once. And the only thing I want to change is the concentration of A. So, for example, here's what I'm going to do. I'm going to pick reaction 4 and reaction 3. Mainly because of the fact that that's going to keep my B concentrations the same. It's going to take my C concentrations to the same. And then the only thing that's going to change is my rate. Now, when you do this, listen to me. This is a process. You are showing what reactions that you chose. This is not randomly writing down numbers and go, oh, a miracle happened. This is what I got. No. Okay? This is a process. So, I am going to show you the full-blown thing, but I will show you there is a little shortcut that you can take. Okay? So, I'm going to choose reaction 4 and reaction 3. Now, I'm going to put our reaction 4 over reaction 3. And the reason I'm going to do that is because that way, on my rate, I'm going to take 0.08 and divide that by 0.02. Okay? That way I avoid fractions, which I want to do like, you know how I feel about fractions. So that's why I'm going to choose 4 over 3. So I'm going to have two advantages putting 4 over 3. Number one, the rate is going to be 0.080 divided by 0.020. Okay? That's going to allow me to not have a fraction there. Then, I'm going to come in here, I'm going to put, okay, hey, this is the concentration of A, which is 0.20. That's associated with reaction 4. I didn't just randomly make up the number. That's what that is. And then I've got 0.20, 0.10. Okay? So this is my A value, that's my B value, that's my C value. And then down below that, I've got reaction 3, which is going to be 0.10, 0.20, and 0.10. Okay? So all of these are going to cancel out. So if you're actually taking the AP exam and they ask you to do this process, even though those are going to cancel out, you write them out. Okay? Now, for the sake of me, if you want to show those in the full-blown thing, you can, but as a minimum, I say again, as a minimum, I want to see at least this step. I want to see which reaction that you chose, and then the values of the rate and the values of the concentration. So, if you take 0.08 and divide that by 0.02, you get 4. And then you take 0.1 and divide that by into 2, you get 2. So 2 raised to some power is going to equal 4. So x equals 2. So what that tells me is that this is what we mean is that we're going to say that this reaction is second order with respect to A. So what this means is because this is squared, if I double the concentration, the rate goes up by a factor of 4. If I triple the concentration, the rate's going to go up by a factor of 9. Okay? So what that tells me is that small changes in the concentration of A are going to have a huge impact later on in terms of the rate. So here's what I know at this point. Some rate is going to equal some K. My A concentration is going to be squared. Okay? I know what X is. I got that one. I'm done with that one. I know what that is. I don't know what y is, and I don't know what z is. So now I want to go after y. So it's the same process. So to go after y, I want to change a situation where I'm going to keep A's the same, C's the same, and I'm just going to change B. So which can I pick that just changes B? 3 and 2. So again, I'm going to put 3 over 2 so I avoid a fraction. So I'm going to be the same process. I'm going to take reaction 3 and divide that by reaction 2. Now, I know what the process is. You don't have to go through and rewrite everything. If you want to, great. Okay? But basically, I chose those because I'm isolating them. So in this situation, I got rate 3, which is 0.020, and the rate 2 is 0.010, and then my B's concentration was 0.2, and that's 0.1. So if I do this math, I get 2 equals 2 to the y. So y is going to equal what? 1. So that's first order. So we say it's first order with respect to B. So now I know what my y value is. So since that's a first order, what that means is that if I double the concentration, and this is what happens, if I double the concentration of B, I double the rate. Because it's first order. If I triple it, it triples. It's just a straight linear relationship. So if it's second order, I double it, the rate quadruples. If it's first order, I double it, the rate just doubles. Cool. Now, the only thing we have left to find is Z. So the only ones I have left are 2 and 1. So I'm going to take rate 2 and divide that by 1, and I've got 0.10, 0.10, and then C is 0.10 and 0.05, so this becomes 1, and this becomes 2 to the Z. So 2 raised to what power is going to equal 1? 0. So Z is 0. So what that means is that 0 order with respect to C. So what that tells me is that C has to be present. You can do whatever you want with C. It has to be there. You can do stoich with it. It's important. It just doesn't change the rate. Okay? Or not say, again, don't go, oh, C is the chemistry of a lesser god. Okay? Okay? C is cool. There. It just doesn't impact the rate. So here's what we've got. So we have R equals K. A is second order with respect to that. B is the first order, so we don't have to put anything up there. Now, there's 2 options you can do with C. One option is that you just leave it out because it's 0 order. Okay, you just don't write it down. But if you do, it's like, man, I don't want C to feel left out. Great. Put C to the 0 power. So you can leave C out, or you can put it to the 0 power. I don't care. Makes me no difference. Now, here's the last thing that we need. We need to find K. Okay? That's the ultimate thing that we're after. So, at this point, pick a reaction. Mara, pick a reaction. 1 through 4. Pick one. 2. Okay. So Mara picked 2. All right? So now we're going to plug in the numbers. So we've got the rate on reaction 2 as 0.1 or 0.010. Now I'm going to write this as molarity per second. that's going to be huge in terms of the units of K. So I don't know what K is, that's my unknown. I have the concentration of A because Mara picked 2, so that's going to be 0.10 molarity. Now I have to really begin to worry about the units now. So that's going to get squared. B is 0.10 molarity, and that's just the first power. And I'm just going to leave C out because it doesn't matter. Okay? Now, in terms of how this is going to play out, your value of K needs 2 things. It has to have the correct numeric value, and it has to have the correct units. So, if you look at this, you're going to have 0.01. Over here, you got 0.1 squared times 0.1. So we're going to divide this by all of that. Okay? So if you do the math, so take 0.01, you do all the math. Mathematically, you get K with the units, mathematical answer of 10. Okay? Now, this isn't uppercase K. This is lowercase k. So don't look at that and go, it's the forward reaction because K is bigger than 1. This is not uppercase K. This is lowercase k. Okay? This has nothing to do with the direction that the reaction is going to go. 2 completely separate things. This is why this is lowercase k and not uppercase K. This is just a rate constant. That's all it is. Now, the tricky part is the units. Okay? This is the tricky part. So, I know that this over here has to be an introduction of time. So I know that K has to be something over seconds. Okay, so any K value has to have some unit of time in it because the concentrations aren't. Okay, those concentrations have no units of time. So the only way that I can just introduce time into this is with the value of the rate constant. Okay, because nothing else has time in it. So it always has to be time. That's where you introduce it in a second. So mathematically, when I take molarity squared times molarity, what do you get? I get molarity cubed. So this part here, out of all of this, I get molarity cubed. So if you want to view this from an algebra problem, I need to end up in molarity seconds. Okay? That's what I've got to end up in on my rate. K has to be something, but over here I have molarity cubed. So I've got to drop my molarities by an order of 2 and introduce time. So there's a couple of options that you can do with it. One option is that you could do, I'm going to put 1 over molarity squared seconds. Okay, so stay with me here. If I have 1 over molarity squared seconds, and I multiply that by molarity cubed, what's going to happen? Yeah, I'm going to cancel out 2 of those. I'm going to get molarity per second. Winner, winner, chicken dinner. Okay? Cool with that. Now, that's one option you can do. You could have written it like this. You could have written it as molarity to the negative 2 over seconds. Okay? Could have done that. But wait, there's more. You could have written it as molarity to the negative 2, s to the negative 1. Done that. Okay? I don't care. All right? Just what you cannot do. You just cannot say, oh, K is 10. This is not uppercase K, which has no units. Lowercase k has to have units. Now, let's play the what if game. If it had been first order with respect to A and first order with respect to B, let's just say, it had been first order with respect to both of them. Okay, nothing was second, it was first order with respect to each one. So this would be molarity squared, because it's molarity times molarity. My rate, in case you haven't figured this out, any rate has to be molarity per second. There's no variation on the rate units. That's always molarity per second. Might be molarity per hour if it's a slow reaction, but generally it's molarity per second. So if this is if this is a second order reaction, okay, second order reaction means that it's molarity squared or the sum of the exponents is 2. So if it's what we call a second order reaction, what do the units of K have to be? Olivia Pruitt.
Dang it. You restate the question.
It was a tricky question.
I bet.
Are you Olivia?
Okay, Olivia Pruitt. I'll restate the question. What if both A and B had been just first order? So that when I take A times B, I just would have got molarity squared. So what units would K have to have so that when I multiply K by molarity squared, I get molarity per second?
Would it be 1 over a meter second? Or I mean, molarity. Oh gosh, dang it.
Right letter, wrong class.
Sorry, I'm in physics headspace right now. Molarity, 1 over molarity second.
Oh! So 1 over molarity second, or meter seconds, that too, okay? Wrong class. You gotta try teaching both of them and try and keep track of it.
Oh yeah.
Okay, so you can do it 1 over molarity seconds, that's cool. You could do m to the negative 1 over s. You could do m to the negative 1, s to the negative 1. I don't care. If you really wanted to get fancy, because molarity is moles per liter, sometimes you'll see this over liters times seconds, and it'll be liters over moles times seconds. Okay? Sometimes you'll see that s to the negative 1. That's just the easiest way. Now, zero order reactions are rare. So if it had been a zero order reaction, and that's just zero order, they're very rare, but they do happen. What that means is that the rate isn't dependent upon any concentration. The rate is what it is. So what units would K have to have then?
Molarity over second.
Yeah, molarity over second. Because that's the only thing that has anything to it. So what you see as the recurring theme is that any units of K has seconds in it. It's always something over seconds. All right? You just have to decide what goes with it. So here's what's going to happen. Okay? So on today's assignment, all of these are going to involve this process. Okay? Where you're going to be given charts of data, and you have to decide which reactions am I going to pick to get them to work out. So stop that for a second, then hand out the assignment.
So you only do as a few problems.